Welcome back to our channel. Today, we're diving deep into one of the most fascinating concepts in physics, space-time. What if I told you that time and space are intertwined in a cosmic dance, shaping the very fabric of our universe? In this video, we'll explore the intricacies of space-time, revealing how it serves as the ultimate cosmic architect. From black holes to gravitational waves, prepare to journey through the universe's most enigmatic phenomena. Did you know that our entire universe was born from the Big Bang, a staggering 13.8 billion years ago? Everything we see today emerged from a singular moment of creation where everything came from nothing. As we peer through our telescopes, we're greeted by the breathtaking complexity of the cosmos, an intricate mosaic of matter that makes up our universe. But it begs the question, where did all of this come from? Matter in the universe doesn't just exist randomly. It organizes itself into an immense cosmic web. Galaxies and galaxy clusters are arranged along vast sheets and filaments, almost as if a cosmic architect has designed this grand structure. At the heart of it all lies space-time, the fundamental fabric that shapes everything from planets and galaxies to atoms and entire cities. Space-time is the essence of our universe, intertwining time and space in a dynamic dance that fuels the expansion of everything around us. It's a concept that can be challenging to grasp, let alone visualize. But scientists are working tirelessly to unlock its mysteries by observing the universe through various wavelengths of light, like the light from the sun, as well as invisible wavelengths like X-rays and ultraviolet. Now, imagine if we could perceive the universe through the lens of the space-time spectrum. What wonders would we uncover? The possibilities are as limitless as the universe itself. Here's a more engaging rewrite of your script. Imagine witnessing space-time itself, bending and warping as objects move through it. It's a fascinating dance. Space-time isn't just a backdrop. It can expand and pull things apart, shaping our universe in incredible ways. The very geometry of space-time influences how we experience reality. Think about it. When you're driving your car, the hills and valleys of the Earth's surface dictate your journey. Similarly, the curvature of space-time determines how light and matter traverse its vast expanse. The rules are elegantly simple. Every object, including matter itself, tells space-time how to curve, and in return, that curvature guides how matter moves. This interaction is what we perceive as gravity. So, gravity is not just a force. It's a consequence of the shape of space-time, directing how matter clumps together to form larger structures. But it wasn't always this way. In the beginning, the landscape of space-time looked vastly different. The very first particles began to alter its shape, creating variations in density. Picture this. One area of space-time has slightly more matter than another. Wherever there's a little more density, gravitational forces begin to pull things together, laying the groundwork for the cosmos we see today. Picture this. A tiny bit of extra mass begins to bend the fabric of space-time just a little more. This subtle distortion creates a gravitational well, causing even more mass to gather in that spot. In the early universe, these denser regions of matter formed deeper curves in space-time. As more mass fell into these gravitational wells, they grew deeper and deeper, creating a runaway effect. Gravity pulled in more and more matter. It's like a cosmic snowball effect. As this accumulation continued, things got heavier, and before you knew it, the first stars began to form. With clusters of stars, galaxies emerged, each a magnificent tapestry of light and energy. These stars didn't just sit there. They lived vibrant lives, burning through their nuclear fuel and eventually exploding in spectacular supernovae. In this process, they forged the heavier elements that would become the building blocks of everything we know today. All of this began with simple fluctuations of energy in expanding space-time. Those tiny ripples transformed over billions of years into the colossal structures we see now: galaxies, stars, planets, and ultimately, the very environments that allow life to thrive. everything we cherish today, from our own existence to the air we breathe, traces back to that incredible journey through the cosmos. The fluctuations in the expansion of space-time set the blueprint for our universe, influencing the evolution of everything we see today. If space-time didn't have the unique property of bringing mass together, we'd be left with nothing more than a thin haze of hydrogen gas, hardly an interesting universe. Without the curvature of space-time shaped by the matter within it, our cosmos would be a bizarre and empty void. Just imagine, no gravity, no force to pull things together, no stars, no planets, and certainly no people. We owe our very existence to space-time, yet even scientists find it challenging to fully grasp its complexities. There's a deep yearning to understand what space-time truly is. We know a lot about it, but at the same time, it feels like there's so much more we don't understand. Believe it or not, space itself behaves like a material, much like this iron sheet. When I place a heavy weight on this metal sheet, you can see how its shape changes and distorts. Similarly, space can warp and carry waves just like this iron sheet does. To make this metal wave, you need to apply a force, and that's precisely what happens in space-time. To create waves in space, you need something incredibly powerful like me and my hammer. Did you see those waves ripple through the iron sheet? Well, waves travel through space in a remarkably similar way, and we call these fascinating phenomena gravitational waves. Gravitational waves are like cosmic vibrations, generated by some of the most intense events in the universe. Imagine the collision of two black holes. When these colossal forces collide, they release an enormous amount of energy, sending shockwaves through the fabric of space-time across the cosmos. By the time these waves reach Earth, they are so minuscule that they're nearly impossible to measure. But in 2015, scientists at the LIGO Observatory made a groundbreaking discovery. They detected those ripples in space-time gravitational waves. The news spread like wildfire, and it quickly became clear that this was the first direct detection of gravitational waves using man-made instruments on our planet. This monumental breakthrough opened a new window into the universe, allowing us to listen to the symphony of cosmic events like never before. We waited so long for those signals. When the moment finally arrived, many of us were in disbelief. I was so skeptical that I found myself diving into conspiracy theories, searching for any explanation that could prove it was all a hoax. But when I finally saw the data, the emotional impact hit me like a tidal wave. It was a moment that I'll always remember, akin to seeing my daughter's face for the first time after she was born, pure, overwhelming joy. All the hard work and dedication we poured into this endeavor culminated in that single moment, and it was absolutely mind-blowing. We could actually hear gravitational waves on Earth. What makes this discovery even more incredible is a fascinating coincidence. The signals that LIGO measures fall within the frequency range that the human ear can detect. We can actually hear the waves shift in frequency as two black holes spiral closer and closer together before colliding. It's like a cosmic symphony. The sound rises in pitch as these black holes dance around one another, culminating in a breathtaking crescendo as they merge. That moment was nothing short of extraordinary. Listening to the ripples in space-time has unlocked a powerful new tool for exploring the universe. For the first time, we are truly hearing gravity, tapping into a sense we never thought possible in our quest to understand the cosmos. With each observation, we're starting to uncover the mysteries that lie beyond our reach. The detection of gravitational waves from colliding black holes is one of the most groundbreaking discoveries in astronomy in the last century. It's difficult to overstate the significance of this advancement. It's akin to the moment when Galileo first aimed his telescope at the stars, unveiling a new realm of knowledge. Now, we have an entirely new window into the universe, one that promises to reveal astonishing insights about the cosmos and our place within it. So, what exactly is space-time? In the simplest terms, space-time is a four-dimensional continuum that merges the three dimensions of space with the one dimension of time. This revolutionary concept was proposed by Albert Einstein in his theory of relativity, which transformed our understanding of the universe. Imagine a fabric stretched across the cosmos. This fabric represents space-time. Objects with mass, like planets and stars, create indentations in this fabric, causing it to warp. This warping effect is what we perceive as gravity. For instance, when the Earth orbits the Sun, it is not just moving through space, but also through the curvature of space-time created by the Sun's immense mass. This elegant theory allows us to comprehend phenomena like time dilation, where time slows down in stronger gravitational fields. Now, let's delve into one of the most intriguing manifestations of space-time: black holes. These cosmic giants are formed when massive stars collapse under their own gravity at the end of their life cycle. A black hole's gravitational pull is so intense that not even light can escape from it, creating an area known as the event horizon. This boundary represents the point of no return. Within this region, the laws of physics as we know them begin to break down. As matter and energy spiral into a black hole, they contribute to its growth, warping space-time even further. The idea of black holes raises profound questions about the nature of the universe. Are they gateways to other dimensions, or do they simply exist as cosmic graveyards? As we continue to explore these mysteries, black holes remain a testament to the power and complexity of space-time. Another fascinating aspect of space-time is the phenomenon of gravitational waves. These ripples in space-time were first predicted by Einstein in 1916, but were not detected until 2015 by the LIGO Observatory. Gravitational waves are produced by cataclysmic events in the universe, such as the collision of two black holes or neutron stars. As these massive objects merge, they send ripples across the fabric of space-time, traveling at the speed of light. Detecting these waves allows scientists to observe events that were previously invisible to us. It opens up new avenues for understanding the universe's most violent phenomena and offers a glimpse into the dynamics of space-time itself. The discovery of gravitational waves not only confirmed a major prediction of general relativity, but also marked a new era in astrophysics, giving us the ability to hear the universe in a way we never thought possible. Let's turn our attention to another significant aspect of space-time: the expansion of the universe. Since the Big Bang, the universe has been expanding, causing galaxies to drift away from one another. This expansion is not merely objects moving through space. Instead, it's space itself stretching. The discovery of this expansion was groundbreaking and led to the formulation of Hubble's law, which states that the farther away a galaxy is, the faster it appears to be moving away from us. This observation suggests that the universe is not static, but dynamic, constantly evolving. Interestingly, recent studies indicate that the expansion is accelerating due to a mysterious force known as dark energy, which makes up about 68% of the universe. This ongoing expansion raises questions about the fate of the universe. Will it continue to expand indefinitely, or will it eventually collapse in a big crunch? Finally, let's explore the philosophical implications of spacetime. If space and time are interconnected, what does that mean for our perception of reality? Philosophers and physicists alike ponder the implications of a universe governed by spacetime. Some suggest that the traditional understanding of time as a linear progression may be an illusion, with past, present, and future existing simultaneously in a block universe. This perspective challenges our everyday experiences and invites us to reconsider the nature of existence itself. As we continue to unravel the mysteries of spacetime, we find ourselves at the intersection of science and philosophy, where the answers may lead to even more profound questions. One of the most astonishing predictions of Einstein's theory of relativity is time dilation, where time moves slower in stronger gravitational fields. This means that the closer you are to a massive object, such as a black hole or even a planet like Earth, the slower time passes for you compared to someone far away from that object. The effects of time dilation have been measured with extraordinary precision using atomic clocks. For example, a clock at the top of a skyscraper runs slightly faster than one at ground level because it's farther from Earth's center and less affected by its gravitational pull. While the differences in time are minute on Earth, near a black hole, they become profound. In theory, someone who ventures too close to a black hole could experience time at a drastically slower rate than the rest of the universe. A famous thought experiment that demonstrates the effects of space-time and time dilation is the twin paradox. Imagine two identical twins. One stays on Earth while the other travels into space at near the speed of light. According to Einstein's theory of relativity, the twin traveling through space would experience time much more slowly than the twin on Earth. When the spacefaring twin returns, they would be significantly younger than their sibling, having aged much less during their journey. This paradox is a direct consequence of how space-time works at high speeds or near strong gravitational fields. Time slows down. Though it may sound like science fiction, the twin paradox illustrates very real principles that astronauts experience on a minuscule scale during space travel. Wormholes, also known as Einstein-Rosen bridges, are theoretical structures in space-time that could act as shortcuts between distant parts of the universe. These bridges are solutions to Einstein's field equations, but no one has observed one yet. If wormholes do exist, they could allow for rapid travel across vast distances, effectively folding space-time and connecting distant galaxies in an instant. However, there are challenges to the existence of wormholes. They may be inherently unstable, and any object entering one might be crushed by immense tidal forces or cause the wormhole to collapse. Wormholes remain one of the most tantalizing and speculative ideas in the realm of space-time, offering the possibility of faster-than-light travel and even time travel. The speed of light, approximately 186,000 miles per second, is the universal speed limit in space-time. Nothing can travel faster than light in a vacuum. This limitation is intrinsic to the structure of space-time itself. When objects approach the speed of light, their mass increases, and they require more energy to continue accelerating, making it impossible for any object with mass to reach light speed. The speed of light also plays a crucial role in defining the geometry of spacetime. Light's speed remains constant for all observers, regardless of their motion, which leads to strange effects like time dilation and length contraction. As we observe distant stars and galaxies, we are not just looking across space, but back in time due to the finite speed of light. Because the universe is expanding, there's a limit to how far we can observe. This limit is called the cosmic horizon, and it defines the boundary beyond which light has not had enough time to reach us since the Big Bang. Beyond this horizon lies parts of the universe that are forever inaccessible, hidden from our view. As the universe continues to expand, this cosmic horizon grows, pushing more of the universe out of our observable range. This limitation highlights the finite nature of our observable universe within the vast expanse of space-time. Even though we cannot directly observe what lies beyond the horizon, scientists speculate about the existence of multiverses or other cosmic regions with different physical laws. The marriage between quantum mechanics and space-time remains one of the greatest challenges in modern physics. While general relativity describes the large-scale structure of the universe, quantum mechanics governs the behavior of particles at the smallest scales. When these two theories collide, particularly near black holes or in the early moments of the Big Bang, the results are perplexing. Quantum mechanics predicts a universe filled with random fluctuations, while spacetime suggests a smooth, continuous fabric. Reconciling these two frameworks has led to the development of quantum gravity theories, such as string theory and loop quantum gravity. These theories attempt to unify the behavior of particles with the warping of spacetime, offering a more complete picture of reality. The event horizon of a black hole marks the point beyond which nothing can escape, not even light. But what happens to an object that crosses this boundary? The process, often humorously referred to as spaghettification, involves extreme tidal forces stretching and compressing an object into thin strands as it approaches the black hole's singularity. This occurs because gravity near the event horizon is so intense that the difference in gravitational pull between the object's front and back becomes extreme. While spaghettification might sound like a science fiction concept, it is a very real consequence of how space-time behaves near black holes, offering a glimpse into the terrifying power of these cosmic monsters. The Big Bang Theory is the prevailing explanation for the birth of the universe and space-time itself. About 13.8 billion years ago, the universe began as an incredibly hot, dense point that expanded rapidly in a process called inflation. As space expanded, time began to tick, and the universe cooled, allowing matter and energy to form. This initial moment represents the beginning of space-time as we know it. Before the Big Bang, there was no time, no space, at least not in the way we currently understand them. The Big Bang Theory has been supported by a range of evidence, including the cosmic microwave background radiation, the leftover glow from the early universe that provides a snapshot of space-time shortly after its birth. One of the key questions scientists are trying to answer is, what is the shape of space-time? The universe could be flat, curved like a sphere, or saddle-shaped. Observations of the cosmic microwave background radiation suggest that the universe is flat on large scales, meaning parallel lines would never meet and space would extend infinitely in all directions. However, this is still an area of active research. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.